everyone. So, we'll be going over cloud native computing foundations, and I'll be reading through the definition, the word to word definition that's provided by the Linux Foundation. However, we'll go over each of the words and each of the explanations so that you better understand it. The definitions as per is that cloud native computing foundation define it as following. Cloud native technologies empower organizations to build and run scalable application in modern dynamic environment. What is dynamic environment? The environment that keeps changing. So we'll have public environment, then we can have private cloud, we can have hybrid cloud, which is nothing but the combination of public and private cloud. And what are some of the services that we can have? We can have containers, we can have service mesh, microservices, immutable infrastructure, and declarative APIs. Exemplify this approach. So now let's understand what are containers? What is service mesh? So we'll go one by one. Containers are basically nothing, just a lightweight form of virtualization that can bundle an application and its dependencies, for example, libraries and configuration, into one single package. Very easy. Now, let's take this as a packed lunchbox. So, no matter where we take our lunchbox, whether it's our work, to our school, to our university, or to a park, it will always have the same food inside. So we can put, or let's say we can put the vegetables, we can put the fruits, we can add some meat and some kebabs, let's say. So, just like in containers, we have this box where we bundle an application with its dependencies such as libraries, configuration. So, everything is in that box. Now, it's ready to be eaten anywhere that we are going, right? We don't need to have an extra preparation for it. So, we can think of containers as a lunchbox. Now, what are service mesh? Service mesh are basically a dedicated infrastructure layers for managing communication between the microservices. So they can handle service discovery, load balancing, failure recovery, matrices, and monitoring, and some more complex operational requirements such as A/B testing, canary releases, service to service authentication. But let's keep it simple and try to understand what is service mesh in some simple words. So basically, imagine this service mesh as a network of roads that are connecting various delivery trucks, which delivery trucks over here are microservices in a particular city. This would just ensure that all the trucks know where they want to go and how to get there efficiently. And this will monitor the traffic to prevent any sort of traffic jams. So this is an example of service mesh. Now, since I have mentioned microservices again and again, we'll understand what are microservices. So microservices are an architectural style where an application is built as a collection of small independent services. If you understand the word microservices, that means small services, right? Now, it is nothing, just a collection of small independent services that could communicate over a network. And each service is responsible for a specific business function and can be developed, deployed, and scaled independently. So, for example, if a developer need to work on on a particular part of an application, he don't have to rewrite the or need to touch the whole application itself, rather just that particular piece of an application. Now, since we want to explain it in simple terms, let's think it as a architecture. A microservice is an architecture of, let's say, a fleet of trucks. Each has this specialization in different type of cuisine. So let's say one truck is for tacos. Oh my god, I just love tacos. Another one is for sushi. Not a sushi lover, but I know many of you just love it. And then there is another truck of desserts. So each truck has its own specialization, right? And each truck operate independently, but when they are put together, they provide you a complete dining experience. Now that is microservices. Now we have immutable infrastructure. Immutable infrastructure refers as a paradigm where servers and components are never modified. So once they are deployed, we don't modify them. If there is an update or if there is a change that is needed, for example, a new version of a server or a component is built and deployed, then the old one has to be decommissioned. This approach really helps us to ensure the consistency and reliability. So let's take an example. Uh, Imagine we are using some disposable cameras, let's say, for taking pictures. Once the film is used up, you develop the photos and you get a new camera instead of reloading the old one with a new film. This is typically what we used to do, right? So now we are not anymore reloading our old camera. We are just every time we are getting an each new camera, and this each camera that we are talking here is a server. Once this is used and we have any change, this has to be replaced. So this is an immutable infrastructure. Then we, in the definition, we are talking about declarative APIs. So declarative APIs basically allow you to specify the desired state of system rather than the steps to achieve that state. So the system itself basically figure out how to reach and maintain the desired state. This really contrasts with what we usually had was imperative APIs where you specify the each steps to perform the task. Now, an example for that one would be for a declarative API would be, for example, we go to a restaurant, we order a meal, right? We tell the waiter, so we need sushi, for example, or we need gyro, or we need some kebab. Now, you're not telling the waiter steps how you need to make that particular dish. You just go and you just order, and the rest happens at the background, but you at the end are getting the dish. So you're not going yourself in the kitchen and step and cooking it step by step, right? So this is a declarative API where you just tell what the desired state is, and then it will try to reach the desired state itself rather than defining each step by yourself. So now, once again, when we read this definition, it will be a little simpler to understand. So now we know what are containers, we know what are service mesh, we know what are microservices, we know what are immutable infrastructure and declarative APIs, right? So now let's read this definition again. Cloud native technologies empower organization to build and run scalable application in a modern dynamic environment such as public, private, and hybrid cloud, such as containers, service meshes, microservices, immutable infrastructure, and declarative APIs would exemplify this approach. So now we're clear about the concept. We'll move forward and try to understand what are containers, what are other parts of it. Let's talk about two important software architecture patterns. One is monolithic, and then the other one is microservices. Let's start with monolithic architecture. Monolithic architecture is a traditional way of building applications, the one that you can see on your left. In this approach, the entire application is designed as a single self contained unit, which means that all of the functionality and component needed to run the application are included in one large code base and deployed as a single executable file. For example, imagine an e commerce application. In a monolithic architecture, the entire application, including the graphical user interface, product listing, shopping cart, checkout, order processing, everything is bundled together in one big application. Now, let's talk about the advantages of monolithic architecture. First, it's simpler to develop and deploy. Since the entire application is in a single code, based you can develop and deploy it in as one unit. Second, a single executable can be optimized for performance, making it potentially faster. Third, testing the application can be very straightforward since it's a single unit. However, monolithic architecture has also some disadvantages. As the application grows, managing the code becomes more complex. It also becomes difficult to scale different parts of application independently. The whole application must be scaled together, which can make it a bit inefficient. Implementing changes can be slower because even a small update requires redeploying the entire application. And there is a single point of failure. If one part of the application fails, it can bring down the entire application. Now let's move on to the microservices architecture, which at the moment we are interested in. Microservices architecture is a modern approach to building application. In this approach, the application is broken down into smaller, independent pieces called microservices. As you can see in the diagram, there are different microservices as the application is broken down into smaller independent pieces, and each microservice is responsible for a specific function. It can be deployed, developed, and scaled independently from each other. Now, using the same e-commerce example that we gave before, in microservices architecture, there would be separate services for user interface, product listing, shopping cart, checkout, order processing. Each service operates independently and communicates with each other over a network. Let's talk about the advantages of microservices architecture. First, smaller independent services are easier to manage and maintain. You all must agree with this, right? Second, services can be scaled independently based on their specific load. For example, if the shopping cart service is experiencing high traffic, only the service can be scaled up. Third, different teams can work on different services simultaneously without interfering with each other. And changes can be deployed more quickly since the only affected services need to be updated. But microservices architecture also has its disadvantages. Integrating and managing communication between multiple services can be very complex. Managing multiple deployments and ensuring that all services are running smoothly require more operational effort. Communication between services over the network can introduce latency, and it requires a robust network infrastructure and effective monitoring to ensure that all the services are functioning correctly. In summary, monolithical architecture bundles all functionality into a single unit, which is simpler to develop but harder to manage as the application grows. Microservices architecture, on the other hand, breaks the application into smaller, manageable pieces, allowing for independent development, scaling, and deployment, but introduces complexity in integration and operation. So I hope that this helps you to understand difference between monolithical and microservices architecture. If you have any questions, feel free to comment below and we'll talk about it. Let's talk about the characteristic of cloud native architecture and let's go through each one of them step by step. The first one that we have is high level of automation. Automation really means that the we want the computers to do most of the work, right? So in cloud native architecture, we would use automation for our build, test, and deploying of our applications. This is going to really save a lot of our time and would reduce some mistakes. Now imagine that you have a robot and you want it to do everything and you want it to finish very quickly and correctly. The same way we have to think in cloud native architecture. When we are saying high level of automation, we really meant that something can help us with the build, test, and deploy of an application so that there is less human intervention. This means that our software always has to be up to date and less likely to have any errors. Then we have self healing. Sometimes our application can fail or slow down, right? So self healing really means that the system can fix itself automatically without restarting part of the application without human help. Think of this as a computer as a superhero. When it get hurt, it know how to heal itself quickly so that it can keep saving the day. In cloud native architecture, we have the part of application that's, let's assume, stop working. We want a system that can automatically fix it so that everything that we have is running smoothly. Then we have scalability. uh, we all are very much aware of this term, but it really means that we need to handle more user or traffic by adding more copies of the application. This is going to ensure that application run smoothly even when a lot of people are using it. Now imagine you're hosting a big party and you're like more people show up than you expected. Oh my god, now what we are going to do? You quickly set up more tables, more chairs so that everyone can sit in the place. And in cloud native architecture, when we say that when we have more users that are starting the application, the system can automatically create more copies of the application to handle the extra load. This is what is scalability. Cost efficiency. Of course, nobody needs something that is so expensive, right? So cost efficient, it has to be cost efficient. No matter what technology we are talking about, this has to be cost efficient. Cost efficient really means that we are using the resources wisely to save the money. So the system can scale down when not many people are using the application and vice versa. Think this as maybe your electricity bill. So you save more money when you're turning off the lights when you leave a room. Well, that's a good example because I just hate doing that. But yeah, that's where cost efficiency is. So whenever you're leaving a room, make sure that you're switching off the lights. That's an example of cost efficiency. And we can use the same concept we are talking about the cloud native architecture characteristics, because in cloud, it's the same way. When you're not using the system or you are using few resources, make sure that you are you're saving your resources so that you're not charged for that. So saving money on the cloud cost. Now we have easy to maintain. Breaking down an application into smaller pieces, we talked about earlier, we talked about microservices, right? It's really breaking down the application into smaller parts called microservices, which make it really easier to manage and update so that each part of the application can be worked separately without affecting the whole application. Now, imagine your favorite toy is made of small detachable pieces. If one piece breaks, you can fix it or replace it without having to get the whole new toy. So, similar in the cloud native architecture, the applications are broken down to smaller parts called microservices. This makes it easier to update or fix parts of the application without affecting the whole thing. Secure by default. Well, that's my favorite topic. We have to make sure that security is built into the system from the very start. Each part of the application requires authentication, ensuring that only authorized users are there and processes can access it. Now, think it of a house with so many rooms, each locked with its own key. Only people with the right key can enter this specific room. In cloud native architecture, every part of application requires authentication, ensuring that only authorized users and processes can access sensitive information. So these are the characteristics: high level automation, scalable, self healing, cost efficient, easy to maintain, secure by default, make the cloud native architecture powerful and efficient. I hope that gives you a good understanding of cloud native architecture and its characteristics now. Now we are going to learn about auto scaling in the cloud native architecture and how does it really relate to the key characteristics that we have discussed earlier. Now, autoscaling is nothing but just a technique that adjusts the amount of computing resources when your application uses based on the current demand. So, think it as a way to automatically add more power when your application is busy and reduce the power when it is not needed. Autoscaling is like having a magic helper that adds more power to your application when many users are using it and reduces the power when fewer users are using it. This really ensures that the application is always running efficiently. Autoscaling is important because it really ensures that your application can handle more users when needed and save the cost at the same time by reducing the resources when it's not in demand or the demand is low. This relates to the cost efficiency and the scalability characteristic that we have discussed earlier. Now we have, as you can see in the figure, we have vertical auto scaling and we have horizontal scaling. So let's discuss the horizontal scaling, which is scaling out and scaling in. So this means that we are adding or removing instances from your application. Horizontal scaling is like oh, how can I explain? Yeah, maybe it's like more friends to help you when you have heavy object that you need to hold. Each friend would represent an additional instance of your application. So over here you can see we have server A, B, C, and D. So let's assume they are like your friends. And when you have more users that are accessing your application, you add more instances or you add more friends to handle the load. And when the demand decreases, you can remove some instances and help maintain scalability and self healing as your system can adapt to the changes that are in demand. So, this is also referring back to self healing. Then we have, as you can see, we have vertical scaling. So, vertical scaling is like building your yeah, let's say building your muscles so that you can lift the heavy object by yourself. Now you don't need friends in order to help you. You are building your own muscles so that you can carry the object. You increase the capacity of your own existence. So in this case, you are increasing the capacity of the server by giving it more CPU and memory. However, there is a limit to do how much you can increase the capacity, right? So for example, you have 200 kgs that you want to carry on. You cannot do it yourself. You cannot go and try to make your own muscles and then eventually coming back and carrying that particular weight. You have your own capacity, and the same way the server has its own capacity of CPU and memory that it can use. So now this method, when we are saying vertical scaling, would tie back to easy maintenance since you are improving the existing resources, right? So now how this both works, how the auto scaling works. Auto scaling looks at how much CPU and memory your application is using. And if the usage is high, it adds more resources. And if the usage is low, it reduces the resources. It can also use other indicators like the time of the day or maybe a specific business matrix that we have that we can make decisions. So, for example, on Black Friday. There are so many sales going on. Now your e-commerce business need to have more, yeah, need to adapt auto scaling. So we can have different matrices where we can define. So this really ensures that high level of automation is there because we are doing the auto scaling. Remember, we talked about the high level of automation and we said that there should be automation because we need to have less human intervention. Now, this concept of whole auto scaling, that the servers can add more CPU or RAM, or it can scale more servers, this is all referring back to the automation part of it. Now, when we are configuring auto scaling, we have to decide the minimum maximum number of the instances that we want our application to help have. So we can set the rules to when to add or remove instances based on the matrices like CPU usage, and then testing how application behaves under different loads would really help us to configure these settings effectively and maintaining security by default. Remember, we talked about the characteristic security by default. So we need to make sure that we have done the testing, we know how this is going to work, and we're ensuring that our resources are allocated appropriately. In the cloud environment, autoscaling is very efficient because we can quickly add resources within seconds when we need, and we can also scale down the resources to zero when there's no resources that needed. So this is going to have cost efficiency and scalability so that we can optimize the resource usage. Auto scaling also ensures that your application can handle varying levels of demand efficiently, and our horizontal scaling is useful for adding more instances to your application, while the vertical scaling, remember, increases the capacity of existing instances. There is a difference between vertical scaling and horizontal scaling, and both the methods would help us to keep our application running smoothly and cost effectively. And this has to work together so that we can, we can go back and refer to our characteristics and make sure that we have the characteristics for the cloud native approach, which is scalability, self-healing, cost efficiency, automation, maintenance. This is all going to work in our favor, in the favor of cloud native. Let's talk about the concept serverless. So, what is serverless computing and how the serverless architecture looks like? First, before we move any forward, I want to clear the most common misconception that we have from the word serverless. Initially, when I started reading about it, like serverless, I was like, do we have no servers in it? Or how does this is going to really work, right? So, no, it does not mean that there are no servers involved. It just means that the key idea behind is that you still need servers. But you, as a developer, you don't have to manage these servers yourself. Instead, you just focus on writing your application code, and the cloud provider takes care of everything else. And really think it of as a server, less management from your perspective. Here's how the serverless computing works. So you write your application code and upload it to the cloud provider. The cloud provider then automatically chose the right environment to run your application. This really means that you don't have to worry about setting up the networks, the virtual machine, and the load balancers. Now, there's something that is called function as a service, and most of the cloud provider offers serverless runtime known as function as a service. With function as a service, or FaaS, you can basically deploy software simply by uploading the code and providing the container image. The cloud provider would go ahead and abstract all the underlying infrastructure allowing you to really focus solely on the code itself. Now, auto scaling. Auto scaling is actually one of the core component or the core concept of serverless computing because it automatically adjusts the resources based on the demand and often triggered by the events like incoming requests. This means that you only pay for what you use, making it less cost effective, very cost effective, I'm sorry. And if your application gets sudden spike in the traffic, the cloud provider will make sure that it scale up the resources. If the traffic drops, it will scale down the resources. Then we have practical benefits. Serverless computing can be used alongside other cloud computing models, so it really allows for fast deployment and is excellent for testing and the sandbox environment. So, for instance, platform like Knative extended Kubernetes with serverless capabilities, which is very useful for private clouds and on-prem environment. One challenge with the serverless technology is that it lacks the standardization across different cloud providers. So it makes really hard to switch between platforms. However, Cloud Events is one of the projects that is working to standardize how the event data is structured, simply event driven architecture across multiple platforms. So, in summary, when we are talking about serverless computing, it really allows developers to focus on writing the code while the cloud providers handle the infrastructure. It's the perfect for a small stateless application that can benefit from on demand provisioning and auto scaling. Remember, serverless means you don't have to manage servers, the cloud provider does it for you.